All right, everyone. I am here with Katherine Kuchenbecker. Katherine is a director at the Max Planck Institute for Intelligent Systems. Katherine, welcome to the TWiML AI podcast.
Thanks so much. I'm really happy to be here.
I'm really looking forward to digging into our conversation and your work, which is at the intersection of robotics and machine learning. And I'd love to have you start us off with a little bit of background. How did you come to work in the field?
Yeah, so I grew up in California. Actually, although my name looks German and I live in Germany, I'm actually American. And I was raised by a research psychologist, my mom, who's a now retired professor and a surgeon. And I was always fascinated by how things work, and I wanted to create technology that helped people. I also did a lot of art, and I liked writing. So I had many, many different interests, and I was an athlete. And it was that athletics that led me to study at Stanford University, which was also close enough to home, but far enough away. And I studied mechanical engineering. I really enjoyed understanding like both physics, but then how to also design and build things that produce functionality in the world. And I was always drawn more towards like smart systems with sensors and actuators and programming. I actually delayed taking my first programming class because I had heard it was so difficult. All the other athletes, I was a volleyball player, they all said, "Oh, the programming class so hard," and I loved it beyond words.
That's awesome.
And then I took more computer science, I took more electrical engineering, and I decided to stay for a master's degree. And I worked actually as a teaching assistant in a machine shop for 2 years, helping students learn design and manufacturing, like welding and casting bronze and milling aluminum and making parts, staying in the shop late at night, helping. And I really fell in love with working with younger people, helping them design and create things. And I also took this amazing mechatronics class there and like realized I wanted to become a professor and I needed a PhD and I needed a PhD advisor. So I looked around and found a new professor. I was his first PhD student. His name's Günther Niemeyer, and he was one of the first engineers at Intuitive Surgical, a robotic surgery company that most of you probably know. They make the Da Vinci robot. And we got along super well. He was also a volleyball player. And I think, yeah, the mechanical engineering, computer science, electrical intersection is really robotics and then turning it to do something useful, whether that's in health or in consumer products or I mean, we work on so many different things now. And yeah, so I got my PhD there and moved to the East Coast after graduating. I did a brief postdoc at Johns Hopkins University with Alison Okamura, who's now a professor at Stanford. And then I started my faculty career at the University of Pennsylvania in the GRASP Lab, which is a great robotics group. And I was super lucky to have colleagues in several different academic departments. And I was there for 9.5 years. And I mostly do haptics research, robotics. And while I was at Penn, I started doing more research in autonomous robots, giving autonomous robots a sense of touch, sometimes through machine learning. And then in 2017, January, I had the chance to move here to Germany to become a director at the Max Planck Institute for Intelligent Systems. We've been around for about 10 years now. It's a wonderful place to do interdisciplinary research in robotics and AI.
Awesome. Awesome. Tell us a little bit about your research interests. You've given us a taste of them, but what are some of the various uh, areas that you're focused on?
Yeah, so a lot of our work comes back to the sense of touch. So haptics or physical interaction with the world. And I know many researchers study vision, whether it's computer vision or natural vision, or hearing, auditory perception for uh, humans and animals or artificial. We know far less about the sense of touch. And so, from a researcher's perspective, that makes it really interesting because it's still like relatively early days for how do we create artificial systems that can perceive their world through touch. And then we also work on the dual problem, which is actually where I started, which is creating devices and programming them to present high quality haptic sensations to users. And so a lot of the work that we do is inspired by some fundamental insights that like the sense of touch is really important to people and to artificial agents. It's often underappreciated and it's not yet understood that well. And when I talk about touch, I'm kind of talking about two things. And one is your skin, like distributed all over your body. You have cells, receptors that can process different kinds of physical stimuli. So whether
Mhm.
something is touching you or and how big of an area it's covering, if it's sliding across, if it's shaking back and forth, vibration, if it's stretching, if it's warm or cool, taking heat from you. And that's distributed all over your body. So it's like cutaneous sense. And I think you probably already know robots don't usually have any skin or almost any skin. They're really deficient in that.
Mhm.
And then on the other side, there's also your movement through the world, like your joints and the muscles forces. And your brain is constantly combining all that streaming data from all over your skin and the movements you're making with your body to help you understand your own physical, how you're moving through the world, if you're contacting something that's expected or unexpected, and processing that. And the final thing, cool thing about the sense of touch is it's very interactive. So vision is active in that you move around and you get different perceptions of a world, maybe see something from different angles, but touch is even more so because there's a really tight loop between when I touch this glass and I start moving my finger down, I can make movements that are almost not visible and really, really feel something very different or start moving in a different way. And so yeah, I'm fascinated, you can probably tell I'm talking too long about this, by touch-based interactions. And we start from this foundation and work on kind of maybe a few different areas like social, physical, human robot interaction. So giving robots a sense of touch, whether that's actually making sensors for them or how they should process the data, and often to interact with people. Or more specifically, just tactile sensing for robots and for manipulation. We also work on systems where a human is controlling a robot from a distance. So, like the Da Vinci robot, where a surgeon remotely operates these little tools that are deep inside the person. And we work on giving you a sense of touch and maybe using that to provide demonstrations for autonomous robots. And then last, we also work in like virtual reality devices and algorithms to let you feel simulations, like maybe dragging across, on a cell phone, you probably felt some haptic feedback, but being able to
Mhm.
feel textures of surfaces on a cell phone or in virtual reality to be able to make and break in contact with things and to make it feel more realistic.
Nice, nice. I noticed the title of your recent presentation at the iClear conference was haptic intelligence, and I kind of had the sense that that was maybe a double entendre, like the sense of touch or haptic informs our intelligence, but there's also intelligence required to process it digitally. And I think you, in kind of articulating your research portfolio, um, you spoke to the way that that sense kind of informs the way that we or robots move through the world.
Yeah, I think the sense of touch is a little under recognized and it's sort of coming up in importance in robotics. Of course, first, if a robot's standing there, it needs to be able to perceive its environment, to be able to move around and not hit anything. Actually, the goal is often don't touch anything, don't break anything, don't
Mhm.
hurt the person. But then if we want to do something, if we want to manipulate, move things around, pack a box, clean up a room, help a person, robots are going to need to reach out and touch something. And then, like many other researchers, we often turn to humans and animals for some inspiration and are curious about understanding, like scientifically, what is known about the sense of touch. Often, as a researcher, you might have some intuition about how you would design a system. And sometimes that works well, and sometimes it doesn't because there are aspects that you maybe don't properly anticipate. And so a common example is like often a roboticist would think I need to put a force sensor on my robot, like, and that means you have to like cut the wrist and put a force sensor here, and then between the hand and the wrist, the robot can feel the load as it like picks something up. But then it can't. That force sensor here can't feel but things that happen higher up, and it also doesn't give you that much information about where contact is happening. And so skin is distributed and has like it's quite rich and a little bit different from what I would think. Oh, I would need a force sensor,
Mhm.
but maybe also another example is our skin is especially sensitive to transients, to changes in stimuli. And a lot of times, as an engineer, you might look at the levels and think, oh, it's really important that it's at like 2.3 newtons or the illumination, what level that is. But these sometimes the illumination in a room radically changes over the day, and your vision system is adapting, or your touch system is also kind of has these is able to focus in on changes, which are often really relevant and important for behavior or accomplishing what you want. So
Nice. You talked about some of your kind of early, your early days and just liking to build and make stuff. And I just had this wonderful memory of when I was a kid, I was into electronics, and one of the things that I was playing with at some point was a force sensor. It was like some piezoelectric foam or something like that. And you put it between two like printed circuit board elements, and you can, I guess the resistance varies based on the pressure that's applied. I'm
Yeah,
sure
actually, we're working on
hopefully we're a
something
lot
similar
more
to that.
sophisticated now.
We're actually working on something similar to that. We have a
Oh,
paper under review in a human computer interaction conference on something very similar, but to like put touch sensors all over the body of a now robot. You need something cost effective and simple so it'll keep working. But please go ahead. I'm glad you
no,
had a chance to make a force
that was
sensor and play with it.
it. I hadn't thought about that in who knows how long, but it just kind of clearly came back to me. So thanks for that.
I'm glad. I hope that lots of young kids have a chance to test out engineering and computer science. As you were telling your story, I would flashback on. I was lucky that for my 13th birthday, and this was a long time ago. This was in the 1990s. My parents gave me a Dell 386 computer, and it still had like a DOS 5.0 command line and Windows 3.1 that you like ran from the command line. And I like tried absolutely everything possible in Windows and learned all about it, and then learned some weird visual programming language. And I was thought, oh my gosh, this programming thing is really cool. At the time, I had had a knee injury and I had to do physical therapy, and it required me to like tense my muscles for 10 seconds and then pause for 5 seconds and tense. And you always had to sit and watch a clock. And I found that very cumbersome. And I wanted something that would keep that time. And I had to do 3 sets of 10 repetitions. And I wanted to be able to read while I did my exercises. So I used this visual programming language that I'd learned on my new old school Windows 3.1 computer to make a program that would beep to tell me when to start and stop. And so I could read. And I didn't realize until I was later in college and I'd heard all these rumors of how hard programming was. Programming's amazing. It's so powerful and it lets you automate things. And it also, what I later realized, it forces you to think much more clearly. It forces you to think like a computer and be extremely logical. So
Mhm.
I think that's maybe why I fell in love with it as a bachelor's student, as an undergrad.
That's awesome. That's awesome. So tell us a little bit more about kind of where machine learning comes into the picture when you're thinking about haptics.
Yeah. So, I mean, machine learning is a wonderful tool, especially for understanding patterns that are too complex for us to see with the eye. I come from more of a mechanical engineering background. We believe in physics, we believe in Newton's second law, and lots of things. We can we can write out equations of motion and then try to predict how things will behave. But I think we have to make a lot of assumptions like linearity, or yeah, we have to sometimes you have to simplify things so much to make these equations work. And like all models, all of these, like even no matter how beautiful they are, they're all going to be wrong at some point. And the real world is dirty and messy and complicated and not linear and not even not very well behaved. And so then if we want to have a robot or a system that's going through the world and physically interacting with things, for example, we work on designing and creating tactile sensors that incorporate machine learning in the flow. We can do much more if we can free ourselves of some of these really rigid physical assumptions and open things up. But then we need a tool to really understand those complicated mappings and nonlinear transformations. And yeah, so the very, very first project I did that involved machine learning was a DARPA-funded project when I was an assistant professor at the University of Pennsylvania. It was a collaboration with Trevor Darrell, who's a computer science professor at Berkeley. Peter Beal and Tom Griffiths and some other people were also on the bigger project, but I worked closely with Trevor on, it was a grounded language acquisition for robotics. So can we enable robots to associate words with their physical sensations? And there were other cool parts of the project where they were working on verbs like seeing, actions, and nouns, but we worked on adjectives, like how you would describe how things feel through the sense of touch. And we installed, at the time, state of the art tactile sensors in a PR2, which is a humanoid robot, and had it touch a set of about 60 objects that had many different physical properties, and it touched them in different ways. And we also had humans come and touch the exact same 60 objects and describe them in words and rate them with words. So then we could pick out a particular object from this data set, this set of objects. It's called the pen haptic adjective corpus, I think. Pen haptic adjective corpus. And we would know what words people described and also the frequency with which different people described the words. And then we could have the robot touch the same object in different ways. And we trained simple machine learning. So we did at the time manual feature extraction, and I think we did support vector machines to have the robot be able to have all these classifiers that could touch a new thing and like say, is this slippery? Is this nice? Is
Mm.
this scratchy? Is this soft? Um, and that kind of opened my eyes to how much we could do beyond like me just looking at the signals or trying to write. How can I write a formula for nice or
Right.
scratchy? And would I even want to sit there and try to come up with formulas? It was painful enough to have to come up with features. And now we can automatically figure out what features are and maybe go just end to end. But at the time, even that much was really powerful that we could then bring new objects to the robot and have it touch it, and it would give labels. It would tell us how would it describe this object, and
Mhm.
it was actually pretty good. And I thought, this is fun. We should do more stuff like this. And so that's where it began.
That's awesome. So much of the emphasis, and you alluded to this earlier, in machine learning and robotics is around vision, and the application of computer vision to all different aspects of robotics, from locomotion to grasping to manipulation. Um, are there things that you're working on that are, to what degree have we kind of integrated vision and haptics? Is that an area of active research in the field?
It definitely is. I hope that I think robots are now, and they will be increasingly multisensory. That's actually what the workshop that I was in at iClear was about, was multimodal embodied multimodal embodied intelligence or learning, I think. Different senses that a robot or a human has provide different kinds of information from in the world. And I'm convinced, not everyone is convinced, but that having some touch sensing and probably audio also will greatly benefit agents, robotic systems in the future. They have to have vision. There are a few different places where there's crossover or synergy. And one I briefly alluded to is we have created a tactile sensor. It's under review now, so I can't talk too much about it. I showed a little video just of some preliminary results during my talk at iClear. And here we're actually using a camera, like many others have been, to doing a vision-based tactile sensor. And we're basically, then we have a soft structure. This is joint work with Georg Martius and his PhD student Juan Bosan at the Tübingen site of our institute, Max Planck Institute for Intelligent Systems. And so we built a soft structure that has a camera that's looking inside and can see the deformations of where the soft sensor has been being touched. And many others have made beautiful, maybe thin or other shaped sensors. And we tried to make one that was basically the shape of your human thumb, so three-dimensional and can feel on all sides.
Hmm.
And here we use a camera to capture simultaneously the deformation field, but not even the deformation field, just the pixel values all over what's seen inside with some structured lighting. And then Juanbo and Georg created a beautiful deep learning architecture. And we have a little robot that goes around and pokes on the finger, and we get all this data to know exactly where it's been touched when. And it can then generalize, and we can touch it on the outside, and it can show us a map of all the forces it's feeling, and not just normal direction indented, but shear also. So if you push in and you slide along it, it can feel you're pushing up or down. It can tell if you're touching it in a large area or small area, or if it's touching something in that way. And so here's an example where we're taking great stock commercial off-the-shelf good camera and then adapting deep learning, like vision-based deep learning, but the thing we're learning is something haptic, and it actually works pretty well. And I think some other researchers around the world have done similar things. And then certainly, like I was already saying before, robots should combine what they see in the world with what they feel. I'm not working in that so much right now, but except in like rather primitive ways. But I think it's beneficial for sure.
And can you speak to with that previous project you mentioned, how that data or that model might be used? So you've got the robot kind of grasping this thumb shaped thing, and you're using computer vision to um,
I maybe didn't
signal.
explain it well. So there's the sensor eventually will be mounted on a robot, but in the beginning, it's just it's sitting on on a bench, and then another robot, like a almost like
Right.
a 3D printer, a gantry comes around and pokes it. And we hope to mount, we plan to. I have a new code-wise PhD student with Georg, who will both be working to miniaturize the sensor and adapt it, maybe bring in other modalities, and then
Ah,
also to put it on a robot so that the robot could move through the world and touch things and learn. So and be able to physically interact in a controlled way with things in the world. And eventually, maybe we imagine robots, whole parts of the robot could be made in this way. Maybe the distal extremities, the fingers, are the most natural components because you don't need that space so much for like joints and wires to be running. I think we'll have a combination of different technologies uh, deployed. You don't need the same precision of and the same richness of tactile sensation like on your back or on your elbow as you do on your fingertips. This is more like a fingertip, finger, hand
got
uh,
it. Got it. I
target.
didn't realize that you were developing the device that would then be the extremity. And so the idea is that the device that's ultimately deployed on a robot would continue to have a vision sensor in it, and you're building a model that would allow. I'm reading your face here. Yes or no?
I think I'm not explaining myself well, Sam. Hey, maybe let me try one more time. It's actually near the end of the day here in Germany, so I may be not functioning on all cylinders. We're basically trying to make a robot finger. Let's imagine we made two of them, and the robot would have these in the hand. There's a camera inside the
Right.
robot's hand, looking through its own fingers and seeing. And yeah, okay, you
So
get it
the
then.
camera is inside the hand that is deforming the thumb, or the camera's inside the thumb,
The camera's
looking at
inside
the
the thumb. The
right, looking
camera
at the
is the sense of touch,
deformations.
looking inside the robot's own body, seeing the skin from the inside.
Yep. And
You got that. Okay.
I got that. And that is what you I think the distinction that I was trying to draw is the camera like a, train time thing, and then you've got something else, or the camera is always going to be there and you're building a model that basically allows the computer to, turn this video signal into something that's more useful from a grasping perspective.
The second, the camera is the transducer. So we have the mechanical structure, the soft mechanical structure that takes the physical contact and is just passively deforming. And
Hmm.
then the camera sees that, and then the deep learning, and it's capturing frames over time. And
Hmm.
then each frame gets passed through this deep neural net, which is based on a ResNet, and then it outputs a force field. So other people, and also in one part of our paper, we worked on just estimating where am I being touched, like output XY coordinates or and the magnitude of the force or something, or how many like. But that framework, I personally, it doesn't lead very far because what if I get touched in one, two, three, four, five, infinitely many? I have a funny
Hmm.
patch. This thinking about discrete outputs, it didn't really work, and so we
Okay.
actually started this project in 2017, shortly after I came here. Sometimes uh, important things or hard things take a long time, and I think it helps to have some patience and persistence and have many projects going in parallel so that some things will bear fruit sooner. Actually, here you see behind me, it always seems impossible until it's done. This is one of my mottos.
Nice.
um, and then yeah, we output this map of basically little points. Each one has a force vector, a 3D force vector, so the robot can reconstruct the agent with that has this thumb, this finger, can reconstruct where it's being touched and the direction the force is happening against it.
So kind
Does
of
that make
like
more sense?
a vectorized point cloud.
Yeah, like a set of points,
Yep.
and each one has a little vector that tells it is it being touched and in which direction is it being pushed.
Got it. Got it.
Yeah, and it was trained. So the training data comes from a little thing poking it at all these different locations, and it moves around. And then we have every frame with it new. Okay, a little 4 millimeter diameter indenter touch me here or here or here, and it presses down and it pushes down at different force levels and also laterally. The shear is really important, and it vastly expands like the data you have to collect. It's not just where did I get touched and how hard was it pushing, but also it was translating laterally against my skin. So,
Okay.
but
And so that you have that external robot that's essentially generating the training data for your ResNet. It's known ground truth of what the forces that it's imparting into this new sensor that is the camera and the inside out camera that ultimately we want to use to create the point cloud.
Exactly. Yeah. And there's a force sensor on the robot that's probing our sensor, which is called Insight. I should have said that. I should have given it a name. That we're probing it from the outside, and we know how the force vector and where it's being touched. And yeah, it's been a really fun project. Actually, I really enjoy collaborating across disciplines. So like, I know a little about machine learning. I actually really like math. I really like um, programming. I really like making plots and drawing diagrams and understanding things and learning new things. But it's even more satisfying that rather than trying to fumble through alone, to partner with someone really smart and a few really smart people and learn from them. And yeah, that's I think one of the most rewarding things about being a researcher, like an academic researcher.
Awesome, awesome. You mentioned the importance of having multiple projects going on in parallel so that you can wait out the insights, so to speak, no pun intended. Um,
How
what
long it takes for an insight to arrive, or yeah, go ahead.
are some other projects that you're working on in the lab?
Oh my gosh, I can't even count. I have 15 PhD students, 8 postdocs, 3 research scientists, like 4 or 5 people who recently graduated or recently finished and have faculty positions of their own. Okay, I'll tell you just a few. One, we are making a hugging robot. It's called HuggyBot. My PhD student Alexis Block, she was a master's student with me at Penn. She made HuggyBot 1.0, the first one, which was a lot of fun. Actually, got a lot of press at the time. And then for her PhD, which is through our Center for Learning Systems, which is joint with ETH, she's designed and built from scratch a new hugging robot, HuggyBot 2.0. It can see users. It adapts to you. So it's soft and warm, which is very important. And then it embraces you. It adapts to your body size and your position, and it lets you go when you're ready to go.
Hmm.
We had a paper at HRI, the Human Robot Interaction Conference this year on this. And then we have a paper under review where we did some machine learning to give this robot a better sense of touch and be able to know what the user's doing. So when you hug someone, you don't just stand there and then like back away. You might pat them on the back or squeeze them. And the robot has a pneumatic torso, so an inflated, like a beach toy, inflated torso that makes it soft, and we heat it up. But then it has a microphone and a pressure sensor inside the torso. So we collected a bunch of training data. We had people come in and enter into hug with the robot, and then we told them to pat the robot
Hmm.
or squeeze it or rub its back or do nothing.
Hmm.
And so we have data, I don't know, from 20 something people doing these things in various states. And we also had the robot respond, like pat you back or squeeze you, and got a mapping of like what people prefer.
Hmm.
People who really like being squeezed by a robot. And then we have what we call HuggyBot 3.0, where it does this in real time. So it's feeling its this microphone and pressure data in real time and making judgments of like what did the user do and then deciding how to respond. And it's pretty fun to hug. So that's honestly, I know people, you'll be surprised. Hugging a robot is, we have another study that we just finished that I can't talk too much about. We're still analyzing the data, but it looks like people might even sometimes prefer hugging a robot to hugging a person because there's no social pressure if you hug a robot. You don't have to worry it's going to like judge you. Um, anyway,
I'm
so yeah, huggy
imagining
bot.
I'm
Mhm.
imagining the abstract of the paper saying something like HuggyBot 3.0 achieves superhuman performance
Hugging.
in hug detachment timing or something.
Oh yes,
'Cause that can be
actually,
awkward.
working on hugging robots has been surprisingly fun, and also, I mean, Alexis Block and I have had so much fun. She's going to graduate soon, and she'll start a postdoc in the U.S. and hopes for a faculty career of her own. But this is one of the most rewarding things: is getting a young scientist. She started working with me actually when she was an undergraduate back at Penn, and then yeah, now about to graduate. And when we first came up with the idea of hugging robots, we thought, oh no, that's too crazy. And then we were like, no, we got to do it. And it's been real fun. We have collaborators too at ETH, her co-advisors, Roger Gassers and Otmar Hilligus, who've also been helping with like the computer vision for the robot to see and the evaluation. So stay tuned for more stuff about HuggyBot. There's a little machine learning in there. It has to be real time. That's important for robot perception. Things have to be able to execute in real time. For
Mhm,
haptics, gathering the training data can be hard. You have to bring real people in and have them really hug your robot and not hurt them, uh, and get a big diversity. People are really diverse and behave in strange ways sometimes.
mhm,
Let's see. And then we do a bunch of other human robot interaction, like robots for exercise. I was talking about tactile sensing for robots. Um, we do some things on surface haptics, like on a cell phone, like understanding the physical contact between human finger and the screen. Ah, I mean, I can't even think about some augmented reality for robotic surgery, haptic feedback in robotic surgery. Uh, I don't even know. Like a lot of stuff.
And so does machine learning primarily come into play when you're integrating other senses or doing multimodal work, or is there a degree to which machine learning has become kind of part of the, classical or part of the standard processing, workflow or tool chain for haptic data, if there's enough standardization to even say something like that?
I mean, machine learning plays a role in many of our projects, not in all, but I mean, we have some projects that are really hardware focused, like design and creation, but I think it plays a role in many of our projects, and sometimes it's not even we wrote the machine learning. So, for example, we have a paper at ICRA, the International Conference on Robotics and Automation this year, about the Robot Interaction Studio, which we call a platform for unsupervised HRI, but not unsupervised like a machine learning person would think. We want unsupervised, like no supervisor, no experimenter, no coach in the room. Just we had people come in and play with it's a Baxter robot, so it's a humanoid robot with two arms,
Uh-huh.
and we used a commercial markerless motion capture system called Captury. It's
On the
wonderful.
Baxter or on the person that's playing with the Baxter?
You don't have to wear anything. It's in the room. So we put 10 cameras in the room,
Oh,
and
okay.
they basically function like Baxter's eyes. And it's constantly, so you walk in the room, you don't have to put anything on as a user, and it fits a skeleton to you in like 20 seconds. And then Baxter knows where you are in the room and the pose of your body. And we programmed only for the paper at ICRA, we programmed only that the robot, we had Baxter always track you in the room so that it knows where you are and it's just always facing you. People respond. It has a smiley face, and then we had it do a sequence of like commands, like it was a coach, like it would point around the room and it lift its arms up, and it would like put its hand up like it wanted you to come to it. And then we just looked at, did people do those kinds of things, and then looked at statistics of, did they walk around the room, did they mimic the robot, and we could make heat maps of like where they put their hands and where they went in the room. And actually people, our cues, which were designed just with intuition, were actually reasonably successful, and people were remarkably interested in the robot and had a fun time playing with it. And then in data that hasn't been published yet, we had the robot also notice what the person was doing and try to correct them or guide them and give them feedback on like, and that became even more interesting because then there's this loop. The robot can see what you're doing and can like try to say, oh yeah, you're I'm doing this, but you're doing something else. And it's like, no, lift your arms up, like we're supposed to be doing this exercise. And we did this with like no speech, no instructions to the users. But here's an example where we're using this commercial markerless motion capture system that has deep learning in it, to deliver really great real-time perceptual capabilities to a robotic system, and then using that to create new experiences. Another example I mentioned briefly, augmented reality in robotic surgery. Yeah, we also are doing some computer vision on like so someone else trained the neural network, but we can do computer vision on what the surgeon is seeing to figure out where the tools are, and then use that to create interactive functionality. So those are places where we're really grateful that other wonderful researchers who are experts in machine learning and vision have delivered capabilities that we can then integrate and into interactive systems. And then other times the machine learning is more at the core of what we're doing. And that typically it is more on when we're designing and creating tactile sensors for robots or interpreting information from tactile sensors that robots already have. Yeah.
Nice, nice. Is part of your research, or to what degree, I guess I should ask, is part of your research focused on the kind of the softer side of human robot interaction? Maybe for context, I've had really interesting conversations on related topics to this with Ayanna Howard, for example, talking about this. What I think of as this deference relationship that she's observed between humans and robots. Also, Kate Darling studies this as well.
Mhm.
Is that a explicit focus in your research, or something that you observe while doing other things?
Well, just as a side note, it's great you've talked to Ayana and Kate. I know Ayana and greatly admire her, and I read an article recently about Kate, and I would love to get to meet her someday. And I was really inspired by her advice that we should treat robots, that we should have in our paradigm more that they're like animals than like people.
Mhm.
We do HRI. It's like I actually let the topics that we study in my group mostly be guided by my students' interests, and I'm relatively flexible. Like there's various things I'm interested in. I can get excited about a lot of stuff. I have ideas about a lot of things, and I have had over the last few years, especially since I moved from Penn, more students really interested in human robot interaction. But and yeah, we do human subject studies. We're curious, but maybe something that's different. We don't usually use like a Wizard of Oz paradigm where there's a human controlling the robot. Usually trying to make actual technical systems that are functioning in real time because those constraints need to be overcome, and I want to operate kind of within what could work in the next 5 years, not what it's going to take some
Mm.
well, human level perception is beyond what robots can deliver right now. And so I'm often challenging my students, and we're trying to deliver interactive systems that can function in real time. And I'm certainly a roboticist. When I was a PhD student, there was kind of a joke that in robotics you could get away with proof by video. Like if you made a
Mm.
video of your robot doing something once and like submitted a NICR paper and that one time it was impressive, like no one might ask, does it always do that? How many times did you test it? And this is a bit tongue in cheek, but being able to deliver the same quality of performance over and over, and especially robust to different things that might change in the environment, is really hard.
Mhm.
And in haptics, where we're creating sensations for people to feel, if you read a paper and it's just the technical development and the algorithms or the description of the system, and there was never an experiment with people, the reviewers are skeptical. They don't believe you. Your paper's not going to get accepted. And
Mm.
not only that, you have to like bring real naive people who aren't members of the research team in and have them do stuff and look at both their behavioral, their performance differences, and their opinions in a very unbiased way. It's very scientific. You also need to bring your demo to the conference and let people, experts from around the world, try your system and see if they can break it. Or there's this like pride of I brought a real system. HCI, they do this also, bring real interactive systems and other people try them. And that's how you can gain real credibility as a researcher, by showing your systems live. And you also learn a lot by demonstrating your systems, whether it's to school kids or visiting researchers or at a conference. I strongly encourage demonstrating your work live if you can. It's terrifying, but exhilarating.
Awesome. Awesome. Uh, you also mentioned as we were getting started, and throughout the interview, kind of your passion for mentoring and the personal side of your work and the importance of diversity. And I thought maybe to wrap things up, you can share a little bit of how you think about those topics.
Yeah, thanks. You might have noticed I'm a woman, and there aren't that many women in robotics. There aren't that many women in machine learning. I'm super lucky that I had great mentors and that people gave me opportunities. I worked my butt off to do well, to get into a good university, to learn what I could. I was brought up to really my parents said, like, to those who are given much, much is expected. And like, what are you going to do with your life, kid? Like, where are you going to make a contribution? They're really wonderful people. This was probably the best thing. They gave me wonderful access to education and made it clear that they were interested to see what I was going to do with those opportunities. And
Mm.
and they also did encourage me, even though I was interested in topics that they're both pretty technical. And so maybe I was, yeah, my mom would like fix the sprinkler system. She's a PhD in psychology. In the 1970s, she was programming Fortran on punch cards to analyze experimental data that she had collected. So maybe I didn't drift that far away from my parents in terms of what they do, but in the field that I'm in, mechanical engineering, computer science, electrical engineering, there aren't that many women. So I'm grateful that I was given opportunities, and I believe that young people of all types deserve a chance and to fall in love with this field and to bring their insights and ideas, and to have a chance to contribute. And so that's been something that's been important to me throughout. I have a really diverse team here at Penn, also at Penn and here at Max Planck. My team is more than 50% women, or about 50-50, and from all over the world, and also many different majors, like many different fields of study. And I see every day the benefits of those different perspectives and the cooperation. There can be challenges. There are more cultural, like people from vastly different cultures. I remember a time I met a PhD student who like what had never had a female professor before much, and his policy was he didn't touch women, and but we still managed to have a good conversation, and he did a super good job on his quals, um, and we came to really have a good relationship. So I think it's a good personal growth to work in a diverse group, and I am very passionate about supporting young people, and often that's simply by a few things, like asking them how they are, how's it going, where they want to go in life, and how can I help you? How can I help you get there? What are you aiming for, and what are you excited by? And have you thought about this, or where can we go with that? So I don't know if that's a good answer to your question, but at the end of the day, I think the people I work with, the people I help train, the people I learn from are much more important to me than the actual work that we do. I'm a total nerd. I love the research that I do. I'm very proud of our papers and our findings and our videos, and I do love it. But at the end of the day, I'm even more proud of the people and what they've taught me, what I've learned from them, and the relationships that we build together.
That's awesome. That's awesome. Well, Catherine, thanks so much for sharing a bit about what you and your team are up to. It's been great chatting.
It has been great, Sam. Thanks so much for having me.
Thank you.